Thank you very much. I'm going to talk about the Hamiltonian variational formulation for non-simple thermodynamic system. This is a joint work with Francois. And okay, this is the background. So in the past years, one of the most difficulties in the formulation of non-equilibrium thermodynamics is how to treat the nonlinear constraint, nonlinear non-holodynamic constraint of the entropy production due to the irreversible processes. So we propose a novel Lagrangian variational formulation for such non-equilibrium thermodynamics, which is a natural extension of Hamilton's principle in mechanics. And we have shown that our approach can be applied to various classes of thermodynamic systems, including open systems. On the other hand, we don't know much about Hamiltonian side. So, for instance, there is a naive question: what's a Hamiltonian variational formulation for non-simple or simple, even simple thermodynamic systems? So, the difficulty lies in that the given Lagrangian is always degenerate with respect to thermodynamic variables. So here, so S1 to SP are entropy variables. Here we want to consider two classes of degenerate systems. So one is we assume that Lagrangian is hyperregular with respect to QQ dot. QQ dot are mechanical variables and only degenerate in terms of entropy variables. And second class is much more non-trivial and totally fully degenerate. So maybe I don't have much time for this, but mainly the first class I will explain how to do that. Okay. So this is a schematic figure of non-simple system. So here, a non-simple system is a system in which the system can be regarded as the interconnected system of several simple systems. So simple system means that the thermodynamic variables is only one. So here we consider some S. S is again the entropy variable. So as a whole interconnected system, the non-simple system, so we consider the thermodynamic property of the non-simple system can be represented by S1 to SP. So, and we assume that a mechanical configuration is given by the mechanical variable Q, which is a coordinate in the n-dimensional mechanical configuration space. And we also consider the external force is given by a map TQ times RP to T star Q. RP is a space for the entropy variable. Okay. And we also consider, so inside the system, so we consider some friction and heat conduction between the subsystems. So heat conduction is denoted by JAB, so from subsystem A to B, so which has a symmetric property. Okay. Now, so this is what we already proposed, a Lagrangian variational formulation. So let's consider a configuration space for full thermodynamic systems. So by carry Q is a direct product of Q times V. So Q is a mechanical configuration space and V is the space for extended thermodynamic systems. So I mean that extended means that V is RP times RP times RP. So here we know already RP, the first slot is the space for the entropy, but The second and third RP denote the spaces for the thermodynamic displacement and internal entropy production. So the thermodynamic displacement, whose time derivative is nothing but the temperature of the subsystem. Okay, in this context, so our Lagrangian variational principle is given by the Lagrange-D'Alembert principle, which said that if curves Q, S, gamma, sigma are critical for this variational condition with respect to the chosen variational constraints, so dissatisfied, and with the phenomenological or kinematic constraint here. So notice that this kinematic constraint is non-linear non-holonomic constraints. I will show you abstract setting later. Then the curve satisfies the generalized Lagrange-D'Alembert equations like this. So first one is somehow usual Euler-Lagrange with friction force and external force. But the latter one is a part of our Lagrange-D'Alembert equations, but it's associated with thermodynamics. And dl ds is minus temperature, so Ts dot means the power associated with the entropy production. And on the right-hand side, the first term is the power associated with the mechanical friction, and the second term is the power associated with the heat conduction between the subsystems. So we can develop full equations from this variational principle. Okay. In the abstract setting, so we need to consider the nonlinear constraints for the thermodynamic type in order to incorporate into the abstract variational principle. So I will explain. Just remember, this is a given phenomenological or kinematic constraint. As I said, it is a non-linear non-holonomic constraint, and so it's in general. So it is given in this form, a r x dot. So it's a coefficient, and x dot. So it's quite non-linear, but this is annoying. So because we want to incorporate this guy into our variational setting, how to get the variations to derive the equations. We didn't know that, but in order to treat this nonlinear constraint, we need to introduce a variational constraint set. CV is a subset of TQ plus TQ. The first TQ is the space for the variation x delta x, and the second TQ is the space for the motion x dot. So in fact, our variational constraint is described in this way. So the coefficient is associated with the motion x dot, but we also have delta x. So it's a mixed variational constraint. So by introducing this guy, so mathematically, the nonlinear kinematic constraint can be induced from this CV, so variational constraint, like this. In fact, so we can develop the nonlinear, so we can recover the nonlinear constraints from this condition. Now, this is a typical situation in non-equilibrium thermodynamics. So we call this type of constraint as the nonlinear constraint of thermodynamics type. Okay, this is a key issue. And so this is an abstract variational, Lagrangian variational formulation for nonlinear non-holonomic systems. So we have already shown the concrete setting, but this is an abstract setting. So we have a variational condition, and with the variational constraint together with the nonlinear kinematic constraints. Then the curve, so if the curve is critical for this, then we can get the generalized Lagrange-D'Alembert equation. So the critical curve satisfies these equations. Okay, so far so good. So how to get into the Hamiltonian? So first of all, just consider the case in which Lagrangian is hyperregular with respect to all of so hyperregular on phase space, and so we just consider the Legendre transform, and then the variational Hamiltonian variational constraint is given like this: CB of x and p is equal to CB of x dot, such that so x dot is uniquely determined by this. Then our Hamiltonian variational constraint as well as the Hamiltonian kinematic constraints are given like this. It's quite simple. Okay. Then the abstract Hamiltonian variational formulation for nonlinear non-holonomic constraints are given like this. So we just assume the Lagrangian is hyperregular, so we can define the Hamiltonian as usual. Then so this is a Hamilton-D'Alembert principle, which is an extension of the Hamilton's phase space principle in terms of the Lagrange-D'Alembert analog, and with the Hamiltonian variational constraint and with the Hamiltonian kinematic constraint. So the curve satisfies the generalized Hamilton-D'Alembert equation. This is quite simple. Okay. Now let's consider how to apply the concrete setting for the non-simple thermodynamic system, because the Lagrangian is degenerate with respect to the thermodynamic variable. But here we just consider the special class in which given Lagrangian is hyperregular with respect to mechanical variables. So we assume this. Then very simply we can develop define the Hamiltonian on this space T star Q times Rp for each fixed thermodynamic variables S1 to Sp. We can define the Hamiltonian like this, and via the Legendre transform, but it's a partial Legendre transform by fixing S1 to Sp in such a way that V is uniquely determined from P, like this. Likewise, we can also define the external and friction forces on the Hamiltonian side, and also we can define the Hamiltonian variational constraint like this. So before we use Lagrangian, but here we use dl dsa, so which means that temperature. So minus temperature delta sigma is friction force delta Q. So it's a virtual work due to the friction force, and this is a virtual work due to the heat conduction on the Hamiltonian side. Okay. Then, so this is our Hamiltonian variational formulation for non-simple thermodynamic systems. So here we have the Hamilton's phase space principle, but we extend it for the nonlinear non-holonomic constraint system. So namely, we have the Hamiltonian variational constraint like this, and with the nonlinear Hamiltonian kinematic constraint. Okay, so here we have some additional terms associated with the constraint for the external entropy production rate, but okay, and we impose this guy, and then the critical curve satisfy these equations. So the above two equations are somehow usual Hamiltonian equations with friction and external force. Again, so we also have the thermodynamic evolution equations due to the internal, so in this case internal, but total entropy production rate, you see? So on the right hand side, again, the power due to the mechanical friction, and the second term is power due to the heat conduction. Okay. Now, so we can recover the first law of thermodynamics like this. So it's but by taking the time derivative of the Hamiltonian along the solution curve must be the mechanical power. This is nothing but the power balance, energy balance equations, and corresponding to the first law. And so okay, temperature is like this, and the second law is associated with the total entropy of the system, so which is given by the summation of each entropy. The rate of the total entropy is like this. But in this case, the rate of internal entropy production is the same as S dot. So the internal entropy production I is given by this. You see, so 1 over T. So the power due to the mechanical friction divided by temperature, and also the the power due to the heat conduction divided by T is this. So this rate of internal entropy production is always positive, because so our phenomenological relations or constitutive relation associated with the mechanical friction and heat conductions are given by this, and it's always positive and consistent with the second law. Okay. Now this is a simple example, a non-simple systems example of the non-simple system, but maybe it's simple to understand. But it's a famous program called an adiabatic piston program. Gruber wrote an interesting paper in 1999. So we know how to do by him, but we did in our approach, and so the non-simple system is an interconnected system of sigma 1, 2, 3. So 1 and 2 are single piston, and sigma 3 is a movable rigid rod with some mass. So then we have a Hamiltonian, the kinetic minus plus potential. Potential energies are given by the internal energy associated with the ideal gas inside the pistons. And we also consider the phenomenological relation associated with the friction force inside the piston, and with the heat conduction associated with the movable rod. Okay. Then from the Hamiltonian evolution equations, we get these equations. Okay, and eliminating P, So we can recover the equations of motion which are the same as those obtained in Gruber. So this is the correct answer. Okay. And again, the Hamiltonian is preserved in this context. So we do not have external force. So then the system is isolated. So the energy, total energy, which is Hamiltonian, is preserved. This is a bit interesting because we have friction and heat conduction. Usually they understand such a system is dissipative system, but here we show that this is a conservative system because we complement thermodynamic evolution equations. So because of that, we get these equations, and this is consistent with the first law. And of course, second law is given by this. It's always positive. Okay, the total internal entropy production is always positive. Okay, maybe already time is running out. Just shortly, I will explain. So we have more non-trivial cases. You see, it's a totally degenerate. So it's more interesting. But so to do this, so we need to consider the Dirac theory of constraints. So we define a primary constraint set from a given Lagrangian and its Legendre transform, and we establish some constraint Hamiltonian H tilde. I don't like to mention the detail, but you can see from the equations. But constraint Hamiltonian is not unique, and we can define the total Hamiltonian by complementing the primary constraint set by using the Lagrange multiplier. Then we also apply the generalized Lagrange-D'Alembert principle that I showed in the abstract setting. Just we switch into the total Hamiltonian, and with a variational constraint and the kinematic constraint as well as the variational constraint. Then we get generalized Hamilton-D'Alembert equations. Okay, this is very similar to what Dirac did. So, example, so maybe we need to just see what's going on. And, we consider several. We consider the chemical reaction dynamics in which several chemical species undergoing chemical reactions among them, like this. And okay, so this can be understood in the context of this setting. So because our Hamiltonian or starting point is Lagrangian is totally degenerate because it's just given by minus internal energy. So Q is N1 to NP, NR, so the molar number, and with entropy. These are the thermodynamic variables. So it's totally degenerate. And we cannot define the usual Hamiltonian, but as I showed you, the total Hamiltonian can be constructed like this. So we have some primary constraint set, and so we have internal energy and with primary constraint. Then we define the total Hamiltonian. Okay, I will do very soon. So from the generalized Lagrange-D'Alembert principle, we get naturally the evaluation equations for the chemical reaction, and finally we get these equations. This is the correct answers. Okay. Now, of course, we have the first row and second row in this context. Okay, maybe time is running out. So we have shown the Hamiltonian variational formulation for non-equilibrium thermodynamics, in particular for the non-simple systems. And we have considered two classes of degenerate systems. One is this, and the other one is totally degenerate. And our approach is quite general, and generalized Hamilton-D'Alembert principle is quite useful to understand this sort of non-equilibrium thermodynamics of non-simple systems. Okay, thank you for your attention.
Some questions?
If I understood correctly, you actually introduced dissipation to the system
Yes.
by introducing Lagrangian multiplier, which
Yes.
is somehow connected with entropy.
So you mean, please say again?
You have this, you call it kinematical constraint and
Yeah.
variational constraint. You have two of those.
Yeah, yes, this and this.
And these are these are related to entropy of the system, right?
Yeah.
So, so out of that you get your constraint Hamiltonian.
So here, this is just a Hamiltonian.
Yes.
But for the case of totally degenerate cases, as you say, so we established the constraint Hamiltonian.
Okay.
But this is not constraint Hamiltonian in this setting. Yeah.
If you would like to go to the discrete setting, yeah? How would you, for example, then determine your Lagrange multiplier?
Yeah.
Yeah.
In the generalized case, we need to incorporate the Lagrange multiplier, as you say. So in the discrete setting, maybe we can do as a usual way. But we have to check. But in the Lagrangian context, we do some computations. Already wrote a paper for the simple system. So the non-simple system is more difficult. Maybe we need to see what's going on. Thank you.
So in this system, you have some kind of Lagrange multiplier constraint.
Yeah.
So is it actually it's some kind of DAE? It's some kind of differential equation.
Yeah.
And so do you have for numerics? Do you know if do you know the index of these equations?
That's an interesting question. So maybe in this, so our primary constraint is index 1 or 2. I'm sorry, I don't know for the moment, but it's important to know what's going on in the index. So you mean the algebraic index or differential index?
DAE index, I think.
DAE,
So DAE because we can multiply.
Yeah. DAE. So differential index.
Yeah, because in some settings we can so in Hamiltonian system, in some settings we can say that they are close to 2.
Yeah.
Which is great for
Yeah.
in this case, because
Yeah. So if we consider, so instead of P, Q dot, maybe it's differential index 2, maybe. I'm not so sure. I'm sorry. It's an interesting question.